Good evening, everyone.
Good evening.
Let's start
Good
our
evening, sir.
class for two. Good evening. So it's a little bit of change in my classes. That is, I'm going to take one more class only. This today's class and another class that will be on Sunday. So in these two classes, I will I would like to cover the sensors for industrial automation, starting from old days sensors towards very recent sensors. I will try to cover all these things in these two classes. So let's start with the sensors. So the thing is that in industry you we have seen that different physical quantities like temperature, weight, level, distance, pressure, viscosity, flow rate, torque, speed, density. There's different physical quantities are there, and you will have to measure this quantity to uh, to to make the industry more automated, as well as to maintain the safety, security, and the processes. Uh, I mean the controlling of the processes. So what are the sensor? I think all you have already know that thing. It's a device which provides a usual output in response to a specified measure. Okay, and a sensor acquires a physical parameter and converts it into a signal which is suitable for the signal processing. Okay, so now what are the main detectable phenomena? So in here you will find that the stimulus and the quantity. In stimulus you will find different kind of stimulus are there, and what are the what are the quantity that can be measured to sense or to observe that stimulus. So for example, acoustic, that can be measured by the wave amplitude, phase, and polarization, as well as the velocity. There are some biological and chemical sensors are there. So that can be, for the example, gas sensor, that is the concentration of the gas of the liquid that can be measured to measure. So that is the main principle behind this kind of sensors. Similarly, there are electric sensors, magnetic sensors, optical sensors, thermal sensors, and the mechanical sensors are there. And these are the quantity, and these are the quantity you can measure to yeah, these are the quantity you have to measure to measure the different stimulus. Okay, now coming to the next slide. So once again, the physical principle of the sensing depends on, or these are actually basically governed by this kind of phenomena, where charge, capacitance, magnetism, inductance, resistance, piezoelectric effects, Seebeck Peltier's effects, thermal property of the material, heat transfer, and light. These are the principle, and these are the the thing what you have to understand before going to any kind of measurement. So sensor you have there, and the sensor governed by this kind of physical principles for sensing, and that will enforce that will reinforce you to measure different type of parameters like level, like temperature, like distance, and many more. Now coming to the different types of sensor, you can classify your sensors in different ways. So for the most important thing for this kind of industrial automation, that is direct and indirect. There may be another classifications like active and passive. So in case of direct and indirect, direct sensor can convert a non-electrical stimulus into a electrical signal with intermediate stages. For example, thermocouple. Similarly, the indirect, on the other hand, the indirect sensor, which is a sensor that multiple conversion steps to transform the measured signal into the electrical signal. For example, a fiber optic displacement sensor. And there is a passive sensor. Passive sensor means you have to provide its external voltage or current sources, that is the power sources, to measure the stimulus. On the other hand, active sensors like thermocouple, uh, you don't have to provide any external power sources like battery or the voltage source to operate that sensor. Okay. Now come to the directly to the different kind of physical principle of the sensors. First is the very well known and very old physical principle for the sensors is capacitance based sensor. Capacity measurement. Capacitance, that means I think all heard about the capacitor or capacity. The property of the capacitor is capacitance, and there in the capacitor you there is two metal plates are there, one metal plate over in this part, and just a minute. Okay, you can see that there are two metal plates are there, and in between them there is a dielectric. So that dielectric is so from the capacitor formula, you know that the C is equal to epsilon A by D. So here to you can change the capacity, the area of the capacity plates, that is A. D is the distance between two plates, and that is the epsilon. So you have three parameters. By changing that, you can change the capacitance of a capacitor. So therefore this kind of thing can be used to measure different types of displacement, maybe label, and the different kind of physical parameters. So for example, capacitor as a displacement sensor, you can see that if you change the dielectric medium in between two parallel plate capacitor here, just a minute, problem with this. Just okay, fine. So here you can see that. So this is the metal plate, two metal plates. In between them, if you change the dielectric medium, so in this dielectric medium, you can see that. So this is one dielectric medium, and this is one another dielectric medium. So as you know, C is equal to epsilon A by D. So if you change the epsilon, so you can change the capacitor. Similarly, A can be changed, D can be changed. So therefore, if a inner conductor can be moved in and out, the measured capacitance will be a function of the displacement. Okay. Similarly, a water level sensor can be, primarily a capacitive type, where you can see the dielectric over in this particular area is air, and in this particular area is water. So here you will find one capacitance C1, and here another over here you will find another capacitance C2, and the total capacitance of this coaxial sensor is shown below, is the capacitance of the water free portion plus the capacitance of the water filled portion. So as the level of the water changes, the capacitance also changes, and that can be measured, or that can be calibrated in terms of level. Fine. Now come to the inductor or inductor type sensors. The induction, you know, is a phenomena related to a magnetism in induction, the generation of the voltage from the change in magnetic field. So very basic that we have understand, or we understand the thing in 10th or plus 2 10 12 10 plus 2 classes, that is the Faraday's law. Faraday's law tells us that if there is a magnetic field and if there is a current carrying conductor, so then the induced EMF is proportional to the change of the magnetic field. Okay, so if that is what is the induced EMF, that is E, and what is the change of the magnetic field, that is d phi by dt. Fine. So the electric current sets a circular magnetic field around a conductor, and that magnetic field is proportional to the induced EMF. And if you have an n number of turns in that coil, so that can also be represented as V is equal to minus n d phi by dt. So here you can see that the induced voltage can be measured in terms of B, that is the magnetic field, A is the area, and many more. So thing is that, so induced depending upon the, so if you want to measure, for example, the magnetic particle in your process flow, so there you can measure this by using this inductive type sensors. Now the very popular example of the inductive sensor, okay, that is the kind of called as mutual induction. Not only the self inductance, this is called the self inductance. And there also, if the mutual inductance also possible. Mutual inductance means if there is a current carrying conductor, and in at the adjacent of that current carrying conductor, if another conductor is there, then there is a mutual inductance is created at that adjacent conductor, and that is called the mutual inductance. And in on the basics of this principle, the linear variable differential transducer was made, and here you can see there is a primary wiring. This is the primary wiring, and there is a secondary wiring here. These are two secondary wirings are there. So this LVDT is generally used to measure the displacement, and if you can see there is a soft iron core, so this can be back and forth in this way or in this way. So here if you can see that, so if this core is moved in at the now at the present position, the mutual inductance for this particular coil and this particular coil are same. So what is the output voltage in this particular position? The output voltage will be 0, because the induced mutual inductance means that due to, so as I told you, if there is a current carrying coil and adjacent to there is another current carrying coil, so in that case the mutual inductance is possible, and that comes into the picture. So therefore if this soft iron core moved towards left in this direction, so what happened is there, so in this particular coil, the amount of mutual inductance is reduced. So the EC2, ES2, the voltage induced due to that mutual conductance is also reduced. So there the E0 you will find not equal to 0. That means there is ES1 is greater than ES2, and E0 is not equal to 0. And depending upon this voltage, you can calibrate your position, and you can measure the different position of your sensor. So whatever, for example, you want to measure a displacement, so just add a add something over here. This is the object. If this object move to this direction, the E0 will comes down. So this is the principle of the LVDT. Simple principle. And there is another kind of, this kind of Hall effect sensor, magnetic sensor is there. So this Hall effect sensor, Hall effect means if there is a current carrying conductor. So this is the conductor, and this is the current is flowing. So, and if you put a magnetic field which is perpendicular to the current flow path, see, so this is your current flow path I, and you are putting a magnet which is perpendicular to this direction, this is B, and then what happen is that there is a voltage is generated in the current carrying conductor, and that voltage is known as the Hall voltage, and this voltage is also perpendicular to the direction of both B, that is the magnetic field, and I, that is the current. So this is voltage. So by measuring this voltage, what you can measure is that you can measure the different kind of physical parameters. For example, here you can see is that here you have a Hall sensor. If this magnet comes closer to this Hall sensor, what happen? Your voltage will also increase, because from this Hall effect is actually governed by the rule F is equal to Q V cross B. Okay. So if you increase the if this magnet is comes closer to the Hall sensor, so therefore what happen is the voltage is also increase. So that means what? That means you can measure the presence of any magnetic field, or the movement of the magnet near the Hall sensor. Now coming to the another physical parameter, that is the resistance, and it's a very usual parameter, that is the versatile use of the resistance is there for different kind of application, starting from the pressure measurement to the gas sensing measurement to the biosensor. There are several examples are there where only the resistance or the impedance of the sensor is measured to measure the stimulus. Okay. So now the very basic example, the well-known example of the resistance-based sensor is the strain gauge. Here, this is a particular typical drawing of the strain gauge, and in strain gauge, you can see there is a main two things can be happen. As we know, the resistance is equal to rho L by A, where the L is the length of the coil. So this is the kind of coil you may have a coil or length of the wire, and the A is the effective cross-sectional area of the wire. So if you so if you change this L or A, so you can the R will be varied depending upon the proportionality factor. So that means R is proportional to L and R is proportional to 1 by E. So see, if you put a this strain gauge under the tension, so what happened? The L will increase, therefore R will also increase. On the other hand, if you put this strain gauge under the compression, then L will decrease, that is the length, therefore the R is also decreased. So this kind of strain gauge has a wide application, starting from the load cell to pressure sensor. For torque measurement, there are several kind of measurements are there where only strain gauge are used. There are different classifications are there, like bonded strain gauge, unbonded strain gauge. There are different signal processing circuits are there, like 2-wire measurement, 3-wire measurement, 4-wire measurements, the bridge measurements, and there are many more. And the strain gauge is the well established technology. Till date, it is also used even for the industrial IoT and simple IoT applications. And it is very simple, and it is easy to use and low cost. Now, as I told you, that can be measure pressure, force, small displacement, torque, load, and many more. Now coming to the another important effect, that is the piezoelectric effect. The piezoelectric effect is the generation of electric charges by crystalline material upon subjecting it to stress. There is typical piezoelectric materials are there. For example, that is the quartz, like there are lead zinconate, PJT, and there are Rochley salts and different. These kind of materials has typical typical atomic configuration, which is a periodic in nature, and which is where what happen is that when you apply a force to this kind of material, so what happened due to this application of force? What is force? Force is a kind of energy, and that energy is sufficient to I mean break the electrons, or break the electrons or holes, or whatever the positive or negative charges are there inside the atom. So that is sufficient. The force is sufficient to break the negative or positive ions inside the crystal, inside this kind of material. So what happened when you are so this is the when the force is applied, force is zero. This is the material. For example, quartz, that is the silicon dioxide, SiO2. And when you applying the force in y direction, here you can see the due to this application of force, the positive and negative charges are breaks apart, and they are accumulated at different direction in a y. So you are applying a force in x axis. So this kind of positive and negative source, they are accumulating at the y direction. So positive source at the accumulating at the top, and the bottom the negative ions or negative charges are accumulated. Similarly, it will happen in left in this position. When you are applying force in x direction, that will the charge will, when you are applying force in the y direction, then charge will accumulate at the x direction. So you can see that if you apply a multimeter or a voltmeter, so you can measure a voltage. So that means a voltage is generating by application of force. So piezo means pressure to press, or electric means the voltage. So after the application of the pressure or the force, you can generate a electrical signal. So that's why it's called the piezoelectric. Similarly, the piezoresistive is means after the application of, so strain gauge is a kind of piezoresistive material, because after the application of force, you are changing the resistance of the sensor. So that is the piezoresistive, and this is the piezoelectric. Okay. Now, how can we use the piezoelectric sensor? We can use the piezoelectric sensor to measure the pressure. So because the pressure is proportional, or force is proportional to the generated voltage, so we can measure the pressure by using this piezoelectric crystal. Okay. So this is the crystal which converts the mechanical energy to the electrical energy. Now there are another physical effect, that is the Seebeck and Peltier effect. This Seebeck effect is direct conversion of the thermal energy into a electrical energy. So if there is a temperature variation in two dissimilar material, so there is a possibility of generation of EMF or the voltage. That is the, I mean, the basic fundamental idea of the Seebeck and Peltier effect. Similarly, we have a wide range of electromagnetic spectrum, starting from visible light to infrared, right, UV light. So these are the electromagnetic spectrum, that the radiation of this electromagnetic spectrum can be used as a sensing parameter. Okay, so that can be used as sensing parameter in which is known as the range sensor or the time of flight sensor. The basic principle of this kind of sensor are there is something like that. You have a sensor and a detector. Okay, sender, if you see this over here, you have a sender and receiver. That means sensor and a I mean detector. So sensor, I mean the sender is what it is doing. It will send some light or some ultrasonic wave or any kind of, you may be UV light, you may be visible light, it may be laser, and that will be, if there is a object over here. So after the reflection, that wave will reflect from the object and detected by the receiver or a or a or rejected by a receiver or a detector. So that the reflection, the relation between the the propagating wave, the original wave, this one, and the reflecting wave will be your measurement. That is the so for detection of this object, you can measure, so that this object is actually absorb your radiating signal. So therefore you can easily construct a relation between this after this original wave as well as the reflected wave. It is the very basic principle for any kind of time of flight sensor or the range sensor, where there is a sender and a receiver, and if there is an object, that object will actually uh, I mean absorb some radiation, and that radiation and the relation between the original wave and the reflective wave will give you the objective present or not, and what kind of object and what is the angle, and so different things are there, you can calibrate. Okay, and now here I want to mention one thing is that, so these are the IR wave, that may be some photo laser related thing, there may be ultrasonic sensors, and these are the very basic principle of the time of flight sensor or the range sensor. Okay, and this is the mostly used sensor in the automation industry. For the for the industry nowadays, you will find different IR sensor, different level sensors, different kind of different kind of flow sensor. Those all are basically depends upon the time of flight principle, which is nothing but as I have discussed. Okay, now coming to the, so now, till now we have understand different physical, although there are in beside this there are also there are also several physical explanations are there, physical parameters are there which can be measured, but these are the thing, this is the basic, and most of the this can be covered most of the working principle of the most of the sensor. Now directly come to the process parameters. Suppose you have a boiler, so now you want to measure when this, there is a valve over there, and this is the valve, and you want to measure the pressure, this valve have to be open if the pressure inside this boiler is high, as well as the temperature of this, these things, so this inside this boiler. So what you have to do, you have to measure temperature, you have to measure the pressure inside this boiler, as well as what is the flow of the water, and all these things you have to measure. So let's start with the pressure sensor. In the pressure measurement, you have seen different pressure transmitter, pressure gauges, and pressure switches. What is the difference between transmitter and the switches? Transmitter and the sensors. Sensor only sense the physical parameters, but transmitter is transmit, sense, as well as transmit that data to a remote location or nearer to this sensing position. Similarly, what on the other hand, the switch is, what is the difference between pressure switch and pressure transmitter? Switch, the transmitter will give you the continuous data, but pressure switch is nothing but a kind of on off type of thing. Some level, the pressure is below that level or above that level, that will be determined, and that will be measured by the pressure. So in pressure measurement, you might have heard some nomenclatures. That is, these are absolute pressure. This pressure is reference to zero pressure. So this is the absolute pressure. It is measured. It is reference to the zero pressure. Gauge pressure is the pressure refers to the atmospheric pressure. It may be positive or negative. And vacuum pressure, that is the reference to the atmospheric pressure, and by conversion it is measured in the negative direction. Okay. Now for the atmospheric pressure, you know that is for in general 14.7 psi. So gauge pressure, it may be positive pressure or the negative pressure. If gauge pressure is higher than the atmospheric pressure, so then that is positive, and if it is lesser, I mean, than the atmospheric pressure, then that is the negative gauge pressure. So in absolute pressure measurement, you will find this kind of pressure sensors. So this is the example. Cytrans P300 is a pressure transmitter which is combined with absolute or relative pressure measuring cells with finish mounted diagram. You can see this kind of absolute pressure sensor in industry. Now absolute pressure sensor is can be measured this kind of sensor. Now coming to the differential pressure type sensor, there is an example of Styran PDS3 is a digital pressure transmitter with integral diagnostics function with heart and Profibus PA or field bus foundation protocols, and that is the range from 1 millibar to 700 bar. It works well even with extreme chemical and the mechanical loads or electromagnetics influence. Differential pressure means you have a line. For example, if you want to measure the differential pressure of this water tank, so you have to put a pressure sensor over here where there is a water, and you have to put another pressure sensor over here where there is no water, or there is air. So what the pressure difference in between these two pressure sensor are the differential pressure. Okay. Yeah, and this differential pressure can be used to measure different applications. For example, if you have this is a flow line. If you have a filter over here, by using the differential pressure measurement unit, you can detect the filter is clogged or not. So what does it mean? For example, so you can see that if the filter is not clogged, so the pressure in this region and in this region will be same. But if the filter is clogged, so pressure will be built up in this particular region, and therefore you will find there is a pressure difference between this region and this region. Okay. So now by detecting that differential pressure, so therefore you can detect your filter is clogged or not. Now come to the temperature measurement. There are different temperature sensors are there, like RTD, resistance thermometer detector, thermocouple, resistant temperature detector, thermocouples, thermistors, and many more. And Siemens Citrons TH300 is one of its kind. You can see that this is a RTD based sensors. So in RTD based sensor, this is a passive sensor. This is very well known instrument temperature transmit temperature sensor. In RTD, you will find the PT100. This is the most common type of RTD. So what does it mean? It means that at 0 degrees at room temp 0 degrees Celsius, you will find that resistance of this PT will be 100 ohm. That's why it's called the PT100. Okay. It can also measure the negative temperature. Similarly, you have the thermistor. This is another kind of temperature sensor. There are two types of thermistors are there: negative temperature, negative type, and the positive type. What does it mean? It means there is a negative temperature coefficient and the positive temperature coefficient. For the negative temperature coefficient, if you increase the temperature, your resistance will decrease. For the positive temperature coefficient, if you increase the temperature, your resistance will increase. Okay, there is different kind of materials are there, and depending on this, for example, the semiconductor where has a negative temperature coefficient and the metal has a positive temperature coefficient. Fine. Now another coming to the another kind of temperature sensor, that is a thermocouple, and very well-known temperature sensor for the high temperature application. Thermocouple is generally based on the Seebeck and the Peltier effect, where there is a cold junction and the hot junction phenomena occurs if you have a two dissimilar material, and if you place that two dissimilar material, if that two dissimilar material junction has temperature difference. For example, this particular junction is at 0 degrees Celsius, and this particular junction as at for example, sorry, not this junction. This particular junction is at 0 degrees Celsius, cold junction, and this particular junction at 300 degrees Celsius. So this is the hot junction. So there should be a EMF that is generated, and that EMF can be measured. That EMF or the voltage is proportional to the temperature difference. And that can be calibrated. The generated EMF can be calibrated with the temperature. Okay, and you can see this, the generated EMF is very low. So to increase this voltage, so there is another concept is there, is known as thermopile. So that is the series of thermocouples to increase the voltage of the to increase the output voltage. There are several thermocouples are there in industry, but very popular and well known thermocouple is K-type thermocouple, and all these thermocouple can be can be classified or can be detected by observing their color. For example, the K-type thermocouple is of yellow color and made of nickel chromium, sometimes called the nichrome. So now coming to the different, if you come to the comparative study in between this the temperature sensor, it will be something looks like this. So for thermocouple, that is mainly generally used for high temperature and high temperature measurement, which is around 200, around greater than 2000 degree Celsius, or maybe for example 1000 degrees Celsius. Thermistor is very fast and very highly sensitive among the all sensor, and thermistor and the IC sensor, that is the semiconductor based sensor, some chip based sensor, but this IC sensor is for the low temperature measurement. And among these all sensor, thermocouple, RTD, thermistor and IC sensor, the thermistor has the very fast response kinetics due to its exponential curve. You can see all other sensor has the non-linear curve, but that is not exponential. But thermistor has the exponential curve. So therefore, the thermistor is very fast sensor. But on the other hand, the RTD has a good linear sensor range. So it is very the sensitivity is good, and as well as it is not that much expensive, as well as it is most stable among the all sensors. Now another type of measurement is that is the level sensor. So level can be measured at two types: the point level and the continuous level. Point level is that is the fixed level. For example, you have to measure some level in the water tank. So that is the kind of point level. In the continuous level, that means the level which is continuously changing. That is the continuous level. So these are the sensors like capacitive, ultrasonic, vibrating, rotating paddle switch. These are the examples of the level sensors. So in process control, So the point level measuring is used during the production cycle, and inventory management, the continuous level measurement is used. So now is the capacitive level measurement. You have an example, that is Pointex CLS 200. This is the one example of the point level measurement capacitive sensors, which is a versatile inverse frequency shift capacitive level switch with optional rod or cable choices and configurable output. It is ideal for detection of liquids, solids, slurries, foam, and interfaces. Radar level sensors, the example is Citrans LR250. It is a 2-way 25 gigahertz pulse radar transmitter for continuous monitoring of liquids and slurries in the storage and the process vessels, including high temperature and pressure in a range of 66 feet. Now coming to the another continuous level measurement, measured by the ultrasonic level sensor. Example of it kinds is Citrans probe LU, which is also a kind of 2-way loop powered ultrasonic transmitter for level, volume, and flow monitoring of liquids in open channels, storage vessels, and simple process vessels. Okay. Now, after the level measurement, another type of measurement is the flow measurement. Flow is determined by the determination of the quantity of a fluid, either a liquid, vapor, or gas, that passes through a pipe, duct, or a open channel. So in process, there are several pipes are there where you have to measure the flow. That flow may be expressed as a rate of volumetric flow, mass, or in terms of total volume or mass flow. Okay, there are several flow meters are there. From starting from ultrasonic to the different differential pressure base, flow level measurement, that is Venturi, orifice, Coriolis mass flow. There is Venturi and orifice. There is another kind of mass flow meter, that is the Coriolis mass flow meter. And the magnetic field also used to measure the magnetic, for measure the flow of the liquid which has a magnetic particle. Okay. Now, the ultrasonic flow meter. This is the view of a ultrasonic flow meter or sensor. I will show you a video on this. There is also a electromagnetic flow meters. These are used, as I told you, that is electrically conductive medium, liquids, paste, and slurries. And there is electromagnetic flow meter and sensor. This is the typical example of the electromagnetic flow meter. And the very costly type of kind of mass flow meters are there. These are mainly generally used for gases. So gas measurement, and very this Coriolis mass flow meter is very most costlier, as well as the sensitivity of this kind of mass flow meter and is very high. So here if time permits, I will also show you a video, practical example of the Coriolis mass flow meter. So this is the typical example and typical picture of the Coriolis mass flow meter, which is used in the industry. So these are all about our classes. So let's start with some practical videos. Thus, I have some videos from industries. So where I will show you the, practical measurement, how this measurement can be done by using the sensor, whatever I have told during last 45 minutes. So let's start with level sensor, pressure sensor, and the temperature simultaneously.
This is Shapur from Real Parts. Today in this video I'm going to show you a practical application of a demo application of level. This is Shapur from Real Parts. Today in this video I'm going to show you a practical application of a demo application of level sensors and pressure sensors and RTDs. So this is the setup that we have here. As you can see, we have two tanks. This is just for demonstration purposes. We have two tanks, and with each of these tanks, we have some sort of measurement devices. And I'll start from here at the bottom. You see the liquid into the tank. This sensor is a level sensor that when the level of the liquid inside the tank gets to the level of this sensor sends a signal to the PLC and says, okay, the tank is empty. This one here is a PT100, is an RTD that measures the temperature inside this tank, the temperature of the liquid. You see, this is how RTD works with measuring the temperature inside like a tank. And then if we go up here we have another level sensor, which when the level of the liquid gets to this point, this is just a switch that sends a signal to the PLC and says that the tank is full. So we have two level sensors here, one here and one at the bottom. So one at the bottom, one at the top. The one at the bottom sends a signal. It's just a simple switch that sends a signal to the PLC and says, okay, the tank is empty. And this one sends a signal to the PLC and says the tank is full. Okay, here at the top, we have a level transmitter that measures the level for the whole tank. So we have two switches, one at the top and one at the bottom, that measures the level of the liquid at each point, like at the bottom and at the top. But this one that we have here measures the level of the liquid inside the tank, like as a whole, like the measure of each point, like at the bottom and at the top. But this one that we have here measures the level of the liquid inside the tank, like as a whole, like the measure of the whole liquid, not just at some point, and sends that signal from here. The signal sends the signal to the PLC input, and then on this side of the tank, we have a pressure transmitter. You see now that it shows the pressure as a 120, and this pressure transmitter measures the pressure inside this tank. When the level of the liquid gets high, the pressure here in the tank goes ups and down, and this pressure transmitter measures that pressure, and then again sends the signal from here, sends the signal to the PLC. So we have another tank. So we have two tanks here. We have another tank here. This one is B1 and this one is B2. And we have the same sort of setup for this tank as well. You see, we have a here we also have a level sensor that measures the level of the liquid at the bottom of the tank. When the level gets really low at the bottom, this is only a switch. It sends a 24 volt signal to the PLC input and says, hey, the tank is empty. And then we also have another level transmitter. This one, like the other one that we had here, this one also measures the level of the whole tank, not just at a point. This one measures the level of the tank at the bottom, but this one measures the level of the tank for the whole tank. Okay, so this was just a simple demonstration of how level sensors, level transmitters, pressure transmitter.
There are many types of flow meters available for use in industrial automation. Depending on the product to be measured, whether it's liquid or gas, some basic principles apply to how the meters work. The measured liquid must be water-based or conductive. This makes the mag meter a great choice for wastewater or processed water that is considered fouled or dirty. Mag meters are volumetric meters that have no moving parts. This is ideal for those areas where you wouldn't want to be exposed to the measured liquid while working on the meter. The way a mag meter works is based on a formula called Faraday's formula. Firstly, again, the liquid must be conductive. A voltage is measured that is dependent on the average velocity of liquid, times the strength of the magnetic field, times the length of the conductor. This is the distance between the electrodes. This is all that wonderful science stuff. You know, like E equals mc squared. It's Einstein's theory of relativity. We've all heard of or seen the equation. Many of us don't know what it means. However, the people that do know how to use the equation have used it for both benefit and detriment. For example, the atomic bomb. We don't need to know Faraday's formula to use a mag meter. We don't necessarily even need to know what that formula is. We just know that whomever invented the mag meter used the formula to produce a signal voltage that can be measured by your automation process. While mag meters work based on Faraday's formula, other flow meters work in different ways. For instance, a mechanical flow meter has some moving internal parts which may not fit with specific applications, such as dirty water that carries large particles that may cause damage or obstruct the internal parts. The mechanical flow meter has a rotational device inside, such as a paddle wheel or a propeller. Liquid flowing through a pipe causes the rotation of the internal paddle. which creates a flow rate that is proportional to the rotational speed of the internal paddle. The mechanical flow meter is easier for a layman to understand. Pedaling a bicycle slowly moves you slowly, while pedaling quickly will move you much faster. Direct correlation between how fast the pedals rotate, therefore wheels, and how fast you go down the road. No formula needed, just pedal faster, move faster. Same principle as the internal paddle. The faster it's rotating, the more flow going through the pipe, which in turn sends a graduated signal to your PLC. That's the simplified version, but there are other factors that the manufacturer takes care of for you. Piping size, water temperature, etc., all go into a formula that will correlate the rotational speed with a unit measurement such as gallons per minute. Yet still, there are other types of flow meters. There's Vortex, which measures vortices. Essentially, a sensor tab will bend and flex from side to side as the vortex passes. The bend and flex action will then produce an output frequency that is proportional to volumetric flow. There are also ultrasonic flow meters. The principle behind these meters is that an ultrasonic signal is transmitted downstream or in the direction of the flow, while another signal is transmitted upstream, produce an output frequency that is proportional to volumetric flow. There are also ultrasonic flow meters. The principle behind these meters is that an ultrasonic signal is transmitted downstream or in the direction of the flow, while another signal is transmitted upstream. The delta, or differential time, is used to calculate the velocity of the liquid. That velocity is then used to calculate the volumetric flow through the pipe. As you can see, there are many types of flow meters for various applications. You don't really need to know the formulas and science behind the scenes, but hopefully we have given you some idea of how a flow meter works.
Digital innovation. The most diverse substances are transported and distributed in pipelines every single day. This may include drinking water, fruit juices, oil and gas, as well as chemicals, acids, or alkalis. The fluids flowing through pipelines often display completely different properties. Consequently, there are different principles for their measurement. One such method is flow measurement based on the Coriolis principle. The French physicist Gaspard Gustave de Coriolis set out the physical basis for this measuring principle over 200 years ago. What is interesting is that the Coriolis principle allows the flow of mass to be directly measured. Let's take a closer look at how this measurement method works. A tube is located inside each Coriolis flow meter. An exciter causes this tube to oscillate constantly. Here in an exaggerated example. If there is no flow, the measuring tube oscillates uniformly. Sensors are located at the inlet and outlet and register this basic oscillation precisely. As soon as the fluid starts to flow in the measuring tube, however, additional twisting is imposed on the oscillation as a result of the liquid's inertia. Now, due to the Coriolis effect, the inlet and outlet sections of the tube oscillate in different directions at the same time. The highly sensitive sensors pick up this change in the tube oscillation in terms of time and space. This is known as the phase shift and as a direct measure of sensors pick up this change in the tube oscillation in terms of time and space. This is known as the phase shift, and is a direct measure of how much liquid or gas is currently flowing through the pipe. The higher the flow velocity, and thus the total flow, the greater the deflection of the oscillating measuring tube. The application of the Coriola's measuring principle doesn't stop here. It can also be used to simultaneously determine the density of the flowing fluid. To do so, the sensors also register the oscillating frequency. In other words, how often the measuring tube moves back and forth in 1 second. From the animation, it's clear that a tube filled with water oscillates more frequently than a tube filled with honey, for example, which has a far higher density. Thus, the oscillating frequency is a direct measure of the fluid's density. Both the density and the flow are determined simultaneous density. Thus, the oscillating frequency is a direct measure of the fluid's density. Both the density and the flow are determined simultaneously but independently via the tube oscillation. Endress and Hauser has continuously revolutionized and perfected The most diverse substances are transported and distributed in piping systems every single day. They can include solvents and chemicals, oil and gas. The fluids, one method is flow measurement based on the differential pressure principle. Some 300 years ago, Swiss mathematician and physicist Daniel Bernoulli discovered the direct relationship between the pressure and speed of a fluid flowing in a pipe. Italian physicist Giovanni Battista Venturi also performed experiments on flow, and in 1797 he built the first flow meter for closed pipes, known as the Venturi tube. Here is how this measurement method works. Differential pressure flow meters have an artificial restriction integrated into the measuring tube, illustrated here by the example of an orifice plate. Two holes are located in the pipe wall, one before and one after the orifice plate. Two separate tubes connect these holes to a differential pressure sensor with its two pressure chambers separated by a diaphragm. The tiniest pressure differences in the flowing fluid can be precisely measured. If the fluid is not flowing, the pressure before and after the orifice plate is essentially identical. As soon as the fluid starts to flow, its velocity around the orifice plate increases significantly because of the restriction in the cross-section. At the same time, due to the laws of fluid mechanics, the static pressure at this point decreases. Consequently, different values are detected in the pressure chambers of the sensor, a higher pressure before and a lower pressure after the orifice plate. This pressure difference is a direct measure for the flow velocity, and thus the mass and volume flow in the pipe. The higher the flow velocity, and the resulting drop in pressure around the orifice plate, the greater the differential pressure measured. In numerous industrial applications, the orifice plate covers many needs of flow measurement technology. However, other designs are available for certain measuring tasks to minimize undesired effects, such as excessive pressure loss or abrasion of components due to solids carried in the fluid. This demonstration shows that an abrupt restriction generates severe turbulence in a fluid. Nozzles with a rounded, funnel-like inlet clearly reduce turbulence and thus create less pressure loss. Nozzles are particularly suitable to higher flow velocities or to fluids with abrasive solid particles. Turbulence reduction is even greater with Venturi nozzles. And finally with Venturi tubes, where the restriction is created by longer conical constrictions in the pipe wall. All these designs can be supplied with different restriction diameter sizes, so that the pressure loss and the differential pressure generated can be optimized for the process conditions. Industrial flow measurement using differential pressure has been tried and tested in numerous applications worldwide for about 100 years. With this measuring principle, all liquids, gases, or steam can be measured, even at extremely high process pressures and temperatures. Every differential pressure flow meter manufactured by Andrus and Hauser.
The next point level sensor we will talk about. When you get in your car to go on a drive, you often look at your gas gauge, which is a type of a level sensor. Industries use several different types of level sensors to detect their products. Today, we are going to talk about the different types of level sensors used in the industry. If you subscribe, sensors can be broken and subscribe. This way, you never miss another one. Level sensors can be broken into two classifications: point level measurement and continuous level measuring. Point level measurement indicates when a product is present at a certain point, and continuous level measuring indicates the continuous level of a product as it rises and falls. The sensors for point level indication are capacitance, optical, conductivity, vibrating or tuning fork, and float switch. The sensors for continuous level measuring are ultrasonic and radar or microwave. We will talk about how they work and which applications are best suited for their technology, as well as their limitations in certain applications. Let's talk about point level indication sensors first, starting with capacitance level sensors. A capacitance sensor is a proximity sensor that gives off an electrical field and detects a level by the effect on its electrical field. These sensors are small, less expensive than other sensors, invasive to the product, accurate, and have no moving parts. However, they do have to be calibrated and will only detect certain liquids. Capacitance sensors can be used in liquid storage tanks. A water treatment facility that has storage tanks would be an ideal use for a capacitance sensor. The next point level sensor we will talk about is an optical level sensor. Optical sensors work by converting light rays into electrical signals, which measure a physical quantity of light, then translate it into a measurement. These sensors have no moving parts. They are not affected by high pressure or temperature, are small in size, and can be used in liquid applications. However, if the lens gets coated or dirty, they would require cleaning. They can be used as low-level indicators to prevent run-dry conditions when using oil, coolant, or hydraulics. Another style of point-level sensor is conductivity or resistance. A conductivity or resistance sensor uses a probe to read conductivity. The probe has a pair of electrodes and applies alternating current to them. When a liquid covers the probe, its electrodes form a part on an electric circuit, causing current to flow, which signals a high or low level. The advantages of using a conductivity level sensor are there are no moving parts, they are low cost, and fairly easy to use. The disadvantages are they are invasive, meaning they must touch the product being sensed, they only sense conductive liquids, and the probe will erode over time. Appropriate use for these sensors would be for signaling high or low levels. Vibrating or tuning forks is another type of point level sensor. They use a fork-shaped sensing element with two tines. The fork vibrates at its natural resonant frequency. As the level changes, the frequency of the fork will change, detecting the level. These sensors are cost-effective and are also compact. They are invasive to the product, meaning they have to touch the material to sense the level. These sensors are easy to install and are essentially maintenance-free. They have unlimited uses based on the material that they can sense. Mining, food and beverage, and chemical processing industries use these sensors for their applications. The last point level sensor that we will talk about is a float switch. Float switches use a float, a device that will raise or lower when a product is applied or removed, which will open or close a circuit as a level raises or lowers, moving the float. The advantages of a float switch are that it is a non-powered device. It provides a direct indication, and they are inexpensive. The disadvantages are they are invasive to the product, they have moving parts, and can be large in size. Float switches will only give an indication for a high or low level. They cannot measure a variable level. A great use for float switches is in liquid storage tanks for high or low level indication.
The last video is on time of flight sensor.
New from Sony are back-illuminated time-of-flight 3D image sensors for industrial equipment. Abbreviated as TOF. Pronounced TOF, time of flight is a method of measuring distance to objects based on the flight time of light. Distance to objects are determined from the time it takes emitted light to travel to objects and reflect back to the sensor. TOF captures Z direction along with X and Y directions. This realizes three-dimensional sensing. TOF is useful in inspections that are difficult to see with regular 2D images, such as shape inspections or detecting overlapped objects. As TOF measures distance to objects, it can also be applied to automatic control and collision avoidance of industrial mobilities. TOF will help to meet the increasing demands of an automated society. Let's see what makes Sony's sensor so unique. The key of TOF sensing accuracy is how to capture reflected light efficiently. Sony produced the sophisticated TOF sensor by combining two Sony technologies. Technology to detect reflection light accurately, and a back-illuminated CMOS image sensor. These technologies allowed the Sony TOF sensor to realize outstanding performance. Along with the sensor, a TOF camera's performance also depends on the lens, laser diode, and processor, etc. Here we have a TOF camera. As an example, let's see how the TOF camera can contribute to the logistics industry. Without using a mechanically moving device, a TOF camera can measure sizes with only one shot. Sony's TOF sensor works up to 60 frames per second, making it able to capture faster moving objects than existing 3D cameras. It looks like the sorted boxes are ready to get loaded onto a pallet. Let's look at another scenario using the TOF camera. For carton box picking, robots are required to have instant accurate recognition of the surrounding environment. Compared to existing stereo cameras, the TOF camera has lower system requirements, so it can perform constant high-speed 3D processing inside the camera. Even in situations using multiple cameras, as system loading is light, it's easy to provide 3D data to the robots. A forklift has arrived to carry the stacked boxes. It takes skill to insert forklift forks correctly into the pallet pocket. A TOF camera serves as the eyes of the forklift, which makes it easy to detect pockets. Even while unmanned, the forklift is able to carry the boxes accurately. Now, we will load these pallets onto the trucks waiting outside. Sony's TOF sensor has high environmental robustness and is not easily affected by sunlight. This allows it to assist vehicles to avoid obstacles both indoors and outdoors. Loading is finished and ready for shipment. A TOF camera is laser light itself. Therefore, it can work even in dark spaces. A TOF camera can be used to real-time monitor the volume of cargo inside a truck to realize efficient transportation planning.
Okay, thank you for attention. So if you have any question, you can ask me. I have lots of video, but as we do, time will not permit. I can't able to show all these things, but I have nice video on BMW car manufacturing system. I will share it now in WhatsApp. Please go through it. Uh, okay, any questions? Okay, fine. So good night, all of you. We'll meet again on Sunday.
Okay, sir. Thank you and good night. दिल को हंस